Next question, 7.14. Obtain the answers to A and B in exercise 7.13. Or 1.3. But book it is given obtain the answers A to B. That's a small misprint. You will have to take it as obtain the answers to A and B in exercise 7.13. This is 7.14. It is related to 7.13 in some way. If the circuit is connected to a high frequency supply, 240 volt 10 kilohertz. 7.13 it was again 240 volt, but frequency was 50 hertz. But this sum, it is 240 volt but 10 kilohertz. 10 kilohertz will be 10 into 10 power 3 hertz, which is 10 power 4 hertz. Hence explain the statement that at very high frequency an inductor in a circuit nearly amounts to an open circuit. How does an inductor behave in a DC circuit after the steady state? Very simple. I just given the data of 7.13 sum because we have to refer to 7.13. So you are supposed to find maximum current. For that you should know XL value. XL is inductive reactance L omega. It's given L 0.5 Henry, omega 2 pi F, where F is 10 to the power of 4 hertz. This is half into 2, 1, so 10 power 4 pi. That is inductive reactance. Then of course given resistance is 100 ohm. From the previous sum it was given 7.13. 7.14 refers to the data in 7.13. And impedance root of XL squared plus R squared root of 10 to the power of 4 pi the whole square plus R squared, which is 100 square. You have to simplify this. This on simplification gives you 314.16 ohm. 314.16 ohm is the impedance. So you are supposed to find here I naught. I naught is V naught by Z. What is V naught? VRMS into root 2 by Z. What is VRMS? 240 into root 2. What is impedance? This value. So you can approximate when you are doing calculations reasonably, but here we will see. So this gives you a value of the current, say around 0.011 ampere. So what is the maximum current? 0.011 ampere. What was the maximum current in the previous question? 1.82 ampere. What is the difference? Resistance is same, inductor is same, 13 and 14 sums problems, but only change is in frequency. There the frequency was say 50 hertz, here the frequency 10 kilohertz. That made the current reduce from a value of 1.82 to 0.011 ampere. So it is as if there is no current. So we can say it nearly amounts to an open circuit. In open circuit, we can say the current would be 0, but here it is almost 0. It is similar to an open circuit, we can say, closest to an open circuit, right? Because current has come down to a value of 0.011 ampere. Therefore, high frequency we can say that it behaves as a equivalent to an open circuit. Very nearly it is equal to an open circuit. Then what about time lag? For that you would require phase difference. Let's say tan phi is XL by R. You know this as a formula in alternating current chapter. So XL here is, we already proved XL to be 10 to the power of value of XL, 10 to the power of 4 pi, or 100, 10 square pi. So phi is tan inverse of 100 pi. Phi is tan inverse of 100 pi. That will be equal to around pi by 2, you will get the value to be 1.57 radian. Then how to find time lag? If 2 pi is the phase difference, time lag will be capital T. If phi is the phase difference, what is the time lag? There is a relation between time lag and phase lag. 2 pi is a phase difference, means time difference capital T, which is time period. If phi is a phase difference, what is the time difference? This T, I can write as 1 by F. So 1 by 2 pi F, but F is 10 power 4 hertz. This phi is 1.57. You simplify, you will get the answer 25 microsecond. Therefore, the time lag 25 microsecond. Okay. So we found the data, or we found the answer for the questions in 7.14 relating certain things with 7.13. And already we explained the effect of high frequency in the current. What is the effect? Current has drastically reduced to almost zero value, from 1.82 ampere to 0.011 ampere. Okay. Now he is asking you, what is the effect of? Then you are supposed to prove that. How does an inductor behave in DC circuit after the steady state? After the steady state. The behavior of inductor in DC. So we'll have to do it very carefully. Now the circuit is DC circuit. Okay. Say resistor, inductor. As you close the switch, the current grows to a steady value, because the question is mentioned about steady value. So suppose if you take this as E, this as R, inductance value L, you close the circuit, current grows, it's a transient current, current grows to a steady value. This steady value or final value you can call as I naught. I naught is equal to E by R, steady value of the current. E, R, but no contribution from the inductor. It is as if it is a perfect conductor. It is as if, that means it doesn't offer any opposition, no resistance, nothing. Perfect conductor means no resistance. Only this R is taken. No extra R is not considered here. Under steady state, This is only steady state current. What is the value of the current at any time before that? I equal to I naught. One minus e power R by L into T. This I naught is only the final current, E by R. R by L into T. R by L. This comes under transient current. You don't have to know the derivation. This is the current value before steady state at any instant of time. Okay, in the steady state, only this resistance is considered. Therefore, current I naught is E by R, not E by R plus something else. Therefore, it is as if it is a perfect conductor with no resistance. Even for this, you will get E by R current. It means the inductor which was there, it offers no resistance. So, a perfect conductor under steady state. Any instant before that, current is given by this. So, L will play a role. The current, the current is less. That means not given by R, it is as if some more resistance is there in the circuit, because current becomes less before steady state. Before steady state, current is less. So, R should be more than this. Equivalently, I am saying, it is as if there is more resistance before steady state. As if there is more resistance. But at steady state, only this resistance. No extra resistance. That means it behaves as a perfect conductor, having no resistance. Because he gave the word steady state, and also it is an LR circuit for AC. Now he is asking you to consider in DC circuit, means you take LR circuit in DC, which is the case of a transient current, for which the current at any instant is given by this. Okay. Therefore, under steady state in DC, the inductor behaves as a perfect conductor. Thank you.